Hello, welcome back to trigonometry. We're going to continue talking about vectors. We're going to first look at something called the unit vector, and we're going to talk about something called the dot product. The dot product will be useful over and over again in your application problems. So that's continuing vectors. We're going to talk about these things before we get into applications. A unit vector is a vector that has a magnitude of 1. And there are two very important unit vectors, and I'm going to sketch them on the axes that I have there. But unit vector is a vector with magnitude 1. If we have a vector that starts at the origin, maybe I should do a different color so you can see it better. Vector starts at the origin and goes along the x-axis 1 unit, like that, so that you have basically vector 1, 0, like that. We tend to note that vector as vector I. Now, so that you know that I'm talking about the I vector here, I'll refer to it as I hat. That's something that's commonly done in other classes. And in the book, it's typically going to just be bold I, but I'll go ahead and do I hat here on notes and such. And if you have one that goes out 1 unit along the y-axis, starting from the origin and going along the y-axis 1 unit, so that you've got 0, 1, that one's commonly referred to as J. So I'll go ahead and call it J hat so that you know I'm talking about the unit vector that goes along the y-axis there. Now that unit vector can then be used to help find another way to notate other vectors that are situated on this system. Let's say you have vector, I don't know, let's say you have vector 4, 5. Oops, that should be pointy, sorry. 4, 5. All right, you know that means that you can draw the vector so that the initial point's at the origin, and then the terminal point is at the ordered pair 4, 5. And by using these little pointy parentheses, we know we're referring to the vector. And that's enough information for us to figure out, talk about direction and angle and magnitude or length and so on. But we can also refer to this vector in terms of unit vectors. If you look along the x-axis, you have 1, 2, 3, 4. Basically, you have 4 unit vectors there. So you can go ahead and refer to that as 4 times I hat. Because I hat is 1, 0. Well, 4 times 1 is 4. 1, 2, 3, 4. And 4 times 0 is 0. So 4, 0 is right here. So 4 times 1 is 4. 4 times 0 is 0. And if you look along the y-axis, you've got 1, 2, 3, 4, 5. So you can refer to that as 5 j hat. Notice that it ends at 0, 5. Like if you took j hat times 5, 5 times 0 is 0, 5 times 1 is 5. You get 0, 0, 5. And then this one was 4, 0. Well, you add those two vectors together. If you take 4 I hat plus 5 j hat, that's going to equal 4, 5. You add this vector to that vector, the resultant vector is this one, 4, 5. So you've now got another way you can represent vectors. You can represent them in terms of the unit vector. So if vector v includes AB, then v equals a I hat plus b j hat, where I hat is that unit vector along the x-axis, and j hat is that unit vector along the y-axis. But you can use those to help express the vertical and horizontal components of vector v. Okay, so that little bit of knowledge, you'll be using that as down the line as we go. Okay, next, let's talk about something called the dot product. That if you have a vector u defined with AB, and if you have a vector v defined with CD, then u dot v, so I read u dot v equals a times c plus b times d. So you do product. The first components, the horizontal components, a times c, plus the second components, b times d, and that equals the dot product of the two vectors. So if you have vectors like, if you have negative 5, comma 2, and you're doing the dot product with negative 2, negative 4, what that's saying is to take negative 5 times negative 2 plus 2 times negative 4, and you'll get 10 plus negative 8, or 2. So notice you get a scalar when you do that dot product there. It's also known as the inner product. So we get a real number for this, not a vector. Also called the inner product. And you'll be able to use this inner product to help figure out angles between vectors, and on down the line be able to work with geometry and physics problems. Okay, let's say we have 10 and negative 1 for this vector, and we want to do the dot product with 1, 10. The symbol looks a lot like a multiplication symbol in there, that's multiplication dot. I'll try to make the dot product one bigger than I would a multiplication one. Like here, you know, the multiplication one I made kind of small and kind of small. That's how I'm going to tell the difference. And also you can look at context. If it's between two vectors, then you know you're doing the dot product. Alright, so we got to do 10 times 1 plus negative 1 times 10. So we got 10 minus 10, which is actually 0. You can get 0. That's possible too. Yeah, the dot product has several properties. If you do u dot v, you can actually go the other direction and do v dot u, and the dot product will be the same. You got one that's basically a distributive property. If you've got u dot v plus w, that's going to equal u dot v plus u dot w. If you've got something like a constant times a vector and then dot product with vector, dot product with a vector, then you can do this or this. So if there's a constant involved, there's a sort of associative property there. You try to do dot product with 0, you're going to get 0. Or if you're doing the 0, if you're doing the 0 vector, there's really no, I'll just do it in bold, because there's really no direction to a 0 vector, so I'm not quite sure how I'm going to write this. I'll just do it in bold. And then in your book, it'll do it in bold too, so that way you know you're dealing with the 0 vector. But try to do the dot product of 0 vector with another vector, you're going to get the 0 vector again. And if you do the dot product of a vector to itself, you're going to get the vector's magnitude squared. So those are some properties just to be aware of. You can kind of demonstrate those with just taking some different vectors and trying it out, like with the whole commutative property. Well, we did u dot v here. But if you did it the other direction, if you did like the -2, -4 dot -5, -2, or -5 positive 2, you're going to end up with the same thing. You're going to end up with 2. You're going to end up with the same answer. So you can play around and use actual vectors and show that it works out. This last one's kind of intriguing. Like if you have a vector such as 2, 6, and you want to do the dot product on itself, where you're going to have 2 times 2 plus 6 times 6, so you're going to have 4 plus 12, which is 16. Well, if you take 2, 6 and do its magnitude, that's the square root of 2 squared plus 6 squared. That's the square root of 4 plus 36. So square root of 40. Oops. I really goofed on that. Back here, 6 times 6 was 36. Not 12. I did 6 times 2. Oh boy. 4 plus 36. That's what I get for making these things late. So fix that. Alright. 2 times 2 is 4, plus 6 times 6 is 36. 4 plus 36 is 40. Sorry about that. Alright, now that's the dot product side. But it's going to equal the magnitude squared side. So if we're doing this magnitude and square it, we also get 40. So 40 equals 40. Woohoo! It checks out, especially when you don't make stupid mistakes like I did. So if you caught my stupid mistake before I did, give yourself a brownie point, pat on the back. Woohoo! Alright. So those two sides come out the same, and that's demonstrating this. But if you think about it, if you're doing the dot product on itself, you're taking this first part, squaring it, second part, squaring it, adding them together. And that's basically what you're doing inside the radical sign in the radicand here when you're looking at magnitude. So it's same operations. And then by squaring, you end up eliminating the square root. So you end up with just what was going on in that radicand. Okay, so that's some of the properties. You can play around with those. Now, some things to notice, like the dot product, it can be positive, 0, or negative. It can be any one of those. You can get 0, positive, negative. Like we got a positive one here, positive 2. We got 0 there. But you can also get a negative one as well. It doesn't have to be positive all the time. And the angle between the vectors that you're doing the dot product of is related to the positive, 0, or negative results. So let's actually next develop a geometric interpretation of the dot product, and you'll see how positive, 0, negative ties in with the angles between these vectors. Okay, so if you've got vector u, and let's say you got a1, a2 for vector u. Now so you have vector v with b1, b2. Alright, let's quickly sketch those on a axis system. So, like vector u, let's put it here. Then vector v, let's put it here. So the endpoint for vector u is a1 comma a2, and the endpoint for vector v is b1 comma b2. And then we can look at the vector, the resultant vector between those two, or we can, look between these here. And look at u minus v. If we're doing the subtraction there. Now the angle theta is going to be here. That angle theta is the angle having the two vectors at its sides for which 0 degrees is less than equal to theta is less than equal to 180 degrees. So if you have two vectors, theta is always going to be the angle between the two vectors that's somewhere from 0 to 180. Can't be less, can't be more. So we're looking at positive and less than, non-negative and less than or equal to 180. So with that in mind, we can use the law of cosines here, because basically we have a triangle. We can use the law of cosines here to develop a formula for finding theta. And it's going to be related to our dot product. Okay, so law of cosines, we have the side opposite theta is the u minus v. So that side, the length of it is the magnitude of u minus v. So that squared, according to law of cosine, is going to equal magnitude u squared plus magnitude v squared minus 2 times magnitude u times magnitude v times cosine theta. This is all law of cosines. Okay, so in the case of u minus v, the magnitude, you've got the square root, and then this magnitude is going to be squared. Square root of a1 minus b1 squared plus a2 minus b2 squared. And that whole thing's squared because of the formula. And that equals, okay, magnitude of u is square root of, well, remember this right here is 0, 0. So a1 minus 0 is still a1, and a2 minus 0 is still a2. So you end up with a1 squared plus a2 squared. That whole thing squared. Plus, you got magnitude of v, b1 squared plus b2 squared. Because again, b1 minus 0 is b1, and b2 minus 0 is b2. And that's squared. And then minus 2 times the magnitude. Let's just leave that alone for a second. Magnitude u, magnitude v, cosine theta. Let's leave that there. And you'll see why in a second. Alright, so you have the square root squared kind of cancels itself out, but a1 minus b1 squared, you FOIL that out, you're going to have a1 squared minus 2a1 b1 plus b1 squared plus, and then FOIL this out, a2 squared minus 2a2 b2 plus b2 squared equals, square root and square cancel each other out. You got a1 squared plus a2 squared plus, square root and square cancel each other out, b1 squared plus b2 squared. And you still have the minus 2 times magnitude u, magnitude v, cosine theta. So we're working on getting this statement that's going to help us find cosine theta, or find theta in the end. We can work all this out. So I'll start with the law of cosines. Alright, if we subtract a1 squared from both sides, these will be gone. If we subtract b1 squared from both sides, these will be gone. Subtract b2 squared from both sides, we got that. Subtract a2 squared from both sides, those will be gone. What will we be left with? Let's see, negative 2a1b1 minus 2a2b2 equals negative 2 times magnitude u, magnitude v, cosine theta. Divide everything through by negative 2. You have a1b1 plus a2b2 equals magnitude u, magnitude v, cosine theta. Let me make this paper a little bigger. Well, a1b1 plus a2b2, well, that's really dot product of u and v. And that equals, whoops, didn't mean to draw that. Equals still magnitude u times magnitude v times cosine theta. Well, from there, just do a little algebra, divide by those magnitudes. Cosine theta is going to equal that dot product over the product of the magnitudes. So, and this is true where theta is the angle between u and v. Where 0 degrees is less than or equal to theta, which is less than or equal to 180 degrees. So now we're equipped to find the angles between two vectors. Okay, so let's say we're given vector with 5, negative 12, and we're given another vector 4, 3, and we want to find the angle between these two. Find the theta. Well, if you quickly sketch this out on a grid, you can kind of get an idea about where this vector is heading. So 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, 5, negative 12 is going to put us roughly here. Oops, so we can draw a vector to there. And then 4, 3 is going to put us right here. So we can draw a vector to there. Alright, so then theta has to be from somewhere from 0 to 180. So in this case, theta has to be this angle right here. So that's the theta we're trying to find. Well, cosine theta equals the dot product over the regular product of the magnitudes. Okay. So dot product, we're going to have 5 times 4 plus negative 12 times 3. So that's the numerator. Then on the bottom, the magnitude of u is going to be square root of 5 squared plus negative 12 squared times square root of 4 squared plus 3 squared. Okay, so we got 20 minus 36 up top. And on the bottom we got square root of 25 plus 144 times square root of 16 plus 9. So we get negative 16 on top. We got square root of 169 times square root of 25. So that's negative 16 over 13 times 5, or negative 16 over 65. So to truly find theta, we've got to do the inverse cosine of negative 16 over 65. So call up our trusty calculator. Inverse cosine, negative 16 divided by 65. And there you go. Theta is around 104.25 degrees. Okay. Now on this one, your dot product was negative, so that's something to maybe go back and look at in a few minutes. But don't think about it too hard right this second. Our dot product was negative, and we ended up with a theta that was more than 90 but less than 180. The theta has to be between 0 and 180. Okay, so let's come back to that and discuss the dot product in a few minutes. All right, let's do another one where you have the angle. Let's see here. We're trying to find the angle between, let's say you have vector u, it has 4, negative 3. Vector v has 6, 8. Okay, so to find theta, basically what you're doing is the inverse cosine of the dot product over the product of the magnitudes. Okay, so we're going to do the inverse cosine of, right, dot product, we're going to have 4 times 6 plus negative 3 times 8. And on the bottom we're going to have square root of 16 plus 9 times square root of 36 plus 64. So we're doing the inverse cosine of 24 minus 24. Interesting. Over the square root of 25, which is 5, times the square root of 100, which is 10. So we have the inverse cosine of 0 over 50, or 0. The inverse cosine of 0 is going to give us that theta is 90 degrees. Okay. Well, if theta is 90 degrees, that means the angle between these two vectors is a right angle, which then tells us something else. Interesting, interesting. Let's see here. Let me sketch this out. We need to go out 1, 2, 3, 4, 5, 6. We need to go down 1, 2, 3, up 1, 2, 3, 4, 5. Ooh, should have gone further. 6, 7, 8. Alright, 4, negative 3 is about right here. So if we were drawing that vector, we'd go to here. And 6, 8 is here. So if we're drawing that vector, we'd go to there. So the angle between them, the theta, it turns out is 90 degrees. So it makes a right angle. If these were lines or line segments, we say they're perpendicular, but since they're vectors, we say that they are orthogonal. Orthogonal means they have a 90-degree angle. They're perpendicular to each other. So those two are orthogonal vectors. All right, and a little side note, if your dot product is positive, then your theta is going to be acute. It's going to be from 0 to 9, somewhere between from 0 to less than 90. If your dot product is 0, your theta is going to be right. And if your dot product is negative, your theta is going to be obtuse. which right here, our dot product was 0 up top. We had a 90-degree theta, right angle. Up on this one, the dot product up top was negative, and we ended up with a 104.25 degree angle, which is obtuse. Negative dot product ended up with an obtuse angle. 0 dot product ended up with a right angle. And if your dot product happens to be positive, then you know you're going to have an acute angle. More greater than or equal to 0, less than 90. So just a little something about that. Okay, well that wraps up the unit vectors and the dot product and some of the math behind all of that. So tune in next time. We're going to really use this stuff in application problems. We're going to be using a lot of this stuff that we just learned. And don't be surprised if you keep seeing inverses and keep seeing the law of cosines and all those kinds of goodies. All right, well, thank you for joining us, and I look forward to seeing you again soon.